Everyone, my name is Johanna. I'm a third-year PhD student at MPI-A, and I want to talk about different strategies of finding dormant black holes in our galaxy. As a reminder, our observational picture that we have now is very biased and incomplete. Most of the detections of stellar mass black holes we have come from X-ray accreting or merging compact binaries, but we actually believe that most of the population of stellar black holes should reside in non-accreting dormant systems. In this regime, Gaia has really made immense progress, and with astrometry of billions of stars and a catalog of binary solutions, we have detected the first galactic dormant black holes. However, I think this is just the tip of the iceberg of a much larger distribution, and this is because probably many of the true black holes fell below the stringent quality cuts that were applied to the Gaia orbital solution catalog in DR3. The question is if we can do better and also find black holes that may have been missed. And the good news is that Gaia has published summary diagnostics for a much larger set of stars. So these summary diagnostics can implicitly trace variability and include, for example, the photometric noise or variability, the uncertainties on radial velocities, and this Rover parameter, the fancy chi-squared for the astrometry. And if you have an unresolved binary, this will introduce, the binary motion will introduce excess scatter that will inflate these uncertainties. So the question we were asking is if we can use the summary diagnostics to effectively find new candidates for dormant black hole companions. If we want to do that, we first of all need a good or robust modeling framework to forward model and simulate these parameters. And there, as mentioned before, we have now the Gaia mock package written by Karim that can predict summary statistics and forward model Gaia astrometry. And we showed that if you know the binary parameters, you can robustly infer the summary diagnostics in the catalog, here shown for the astrometric binaries in DR3 with cataloged Rover versus our predicted Rover estimate. What we really want, however, is to solve the inverse problem, so to go not from binary parameters to summary diagnostics, but from summary diagnostics to binary parameters, and look for the binaries that have high inferred companion masses. And to do that, we set up this forward modeling inference framework that for each star assumes it has a companion, a dark companion of some mass, and samples the posterior parameters for this binary. This is a degenerate problem because you only have 2 or 3 summary diagnostics, but you have 7 binary parameters that you would like to infer. However, if we focus on the binary parameters that we are most interested in, which is the period and the companion mass, and marginalize over the rest, the hope is that we can effectively identify promising candidates for black holes. So this is what this looks like for a luminous binary with known parameters, where in order to reproduce the observed Rover and radial velocity uncertainty, we infer a posterior on the orbital period and companion mass that sits right on the true parameters of a low mass companion. This is nice, but I think the nicer part is here. So this is the same machinery applied to Gaia Black Hole 2, so a known dormant black hole system, where we find that we can only explain the high Rover and high radial velocity uncertainty with a very high inferred companion mass. So this was our ta-da moment, and then we went ahead and wanted to apply this machinery to the set of stars that show some variability in Gaia DR3. And we started out by doing this for the giants in DR3, but also applied it later to a set of main sequence stars, which I will come back to in the end. But the giants have the advantage that in most cases they dominate the photocenter motion, and also, as Konov mentioned before, they have a slightly reduced risk of triples, which can be a high contaminant in these cases. So if I infer companion masses and periods with this scheme for all of the giant stars, I end up with a distribution of companion mass and period shown here. And we are most interested, of course, in the high companion mass tail. And it was really nice to see that we recover Gaia black hole 2 and also the candidate mass gap black hole from Lamoste, which are both in this set of candidates. So this gives us some confidence that we are fairly complete, and we could reduce a parent sample of 3 million giant stars to a set of 500 candidates containing the 2 known black holes in this regime, which speaks to a high completeness. But what we also see is that likely we're dominated by contamination from spurious sources. And so to inspect these candidates, we started a follow-up campaign with Ferras to get few epoch high-resolution spectra of these objects. And immediately you can rule out a bunch of them because things go wrong. So you have double-line binaries, you have stars with hot companions, you have some triple systems with short period variability, or stars that don't move at all. But then there's the subset of the candidates that show variability consistent with a binary companion. And ideally, what we would like to do now is infer the orbital periods and parameters for these stars. Usually, you would say with just 3 epochs, this is utterly hopeless and you need to cover the full orbit. The cool thing is that actually, even for these stars with just 3 epochs, in many cases, we can put constraints on the orbital period because we do know the Gaia mean radial velocity and we do know the Gaia radial velocity amplitude. This may look something like this if you incorporate that in the orbit fit. This is nice, but not conclusive in most cases because we don't know the inclinations of these systems, and without those, can't really say what the companion mass is. So it's consistent both with a luminous companion edge on or a compact companion in an inclined orbit. And here we'll wait for DR4 to jointly fit this with astrometry. It would be nice to go from this sample of candidates also to some constraints on the black hole population around RGB stars. But this is a bit tricky given this ambiguous follow-up for some of the candidates, and also we only observed around 100 out of the 500 candidates, so our follow-up is pretty incomplete. The situation is much different for the main sequence sample, which I mentioned in the beginning. So we applied exactly the same thing also to stars on the lower main sequence, and here we have a slightly smaller parent sample, so only around 500,000 stars. And among these, we only find 22 candidates. So 22 is easy to follow up, and we validated 16 of those and could exclude a black hole in all of the 16 observed cases. So this is nice because taking this information and our candidate selection function, which we can model well with Gaia mock, assuming some distribution for black hole masses and periods, we can actually constrain the rate of black hole companions to sun-like stars. And the posterior assembled is shown here on the lower right, but I'll put it for you in relation to other constraints that we have in different period regimes. So we infer roughly an upper limit, 1 sigma, that less than 1 in 100,000 solar type stars has a black hole companion. And it fits in between the constraints we have from ellipsoidal variability for the very short hours to days periods, and the constraints we have for AU scale orbits from the astrometric binary catalog by Pranoff. Yeah, and I think this all is to show that we can, like in the spirit of this session, much is to be learned from the Gaia data beyond just the orbital solution catalog. And we have now this catalog of candidates of dormant black holes plus a limit on the rate of these companions, which I'm very happy about. Yeah, thanks.
Thanks. Wonderful results. It's great to know that there's no black hole in the solar system. You said that 16 of those 22 were the one that you followed up were not black holes, but you didn't mention what you find. Why are they popping up in your selection sample?
Yeah, so I skipped over that. So out of the 16, a few actually have astrometric orbital solutions in Gaia, so I didn't exclude them. They can still end up as candidates. And there we have the full orbit, which tells us they are low mass companions. They can get scattered in there, for example, if they are triples and have an inner high amplitude binary. And I think, and of those we followed up, there was one that just didn't move at all and was consistent with the Gaia mean velocity within 0.5 kilometers per second. So I think that, the chance is very low.
Maybe one more question. What do you expect from DR4?
Yeah, so from DR4, so the first thing I'll do when Gaia DR4 comes out is check the astrometry for all my candidates and hopefully see that some are massive or inclined. I think we always need the joint. So it's good to combine RV follow-up with the astrometry. We'll get RVs also from Gaia, which is good, but you always need to exclude the sp2s. So I think that's good to extend the baseline and already have high resolution spectra. But yeah, we have several more projects for Gaia DR4 where I think this will come in handy.
Thank you.
Thanks. Just a quick question. On your plot showing the candidates, Gaia BH3 seemed to sit somewhere less than 2 solar masses. Now, I believe it's actually 32. So why was it sitting in a strange place?
Yeah, I felt like I had to put it in the plot, but we need to remember that it's kind of a messenger from the future, and we don't really know about it yet. If we only look at DR3, the problem with that binary is that it has a very long period. So the radial velocity variability statistics in DR3 just don't capture it. So from the summary diagnostics, it's consistent with a lower mass companion in a shorter period orbit. And given that that's much more likely in the general sense, we don't recover Gaia black hole 3. May change in DR4 if we have more data.
Kunal, you want to come to set up and we can take one more question?
For any of the objects that could be black holes or could be stars or something else, depending on the inclination angle, are those in short enough orbits that you would expect substantial accretion, especially at periastron?
No, they are generally wider orbits, so from 100 to a few, several hundred.
Well, with the red giant at 100 days, you might actually expect something.
They are also not all far up on the red giant branch, so you have some, so the typical radii, I think in our sample are a few, so 8 solar radii or so, so I think at that point you don't expect accretion. Okay, if they are very eccentric, you might expect, yes, you're right.
All right, let's all thank Johanna again.